Okay, here's our introduction to rational functions. This is, I believe, section 3.5. As a preliminary, we have to substitute some numbers into two different functions. One of them is the y equals 1 over x. The other one is y equals 1 over x squared. So that you can see what's going to happen at each of these different functions, and then you're going to commit it to memory, just like you would do back in chapter 2, where you have a function and you know what the shape is going to be that it looks like associated with that. Now, the domain of either of these two functions are all reals except for 0. And you're going to hear me say multiple times in this video, whatever the domain is, if you exclude a number from the domain, it's going to show itself as a vertical asymptote most of the time, and possibly as a whole. We'll talk about the whole later with examples. We have lots and lots of examples to look at. So the first thing I want to do is focus in on plugging in numbers into that function. So if you put a 3 into the function, you get a 1/3. If you do a 2, you get a 1/2. You put a 1, you get a 1, because 1 divided by 2 or 1 divided by 1. And then where it gets to be slightly tricky for people is when you take 1 divided by a half. Division is the same thing as multiplying by the reciprocal. And so 1 divided by half is going to work out to be a 2. So 1 divided by 1/5 is going to work out to be a 5. And then 1 divided by 1/10 is going to work out to be a 1 times 10 over 1, and that's going to give you your 10. So the same thing will happen with the negatives. You put a -3 in there and you get a -1/3. So if you have positives for both of these, x and y, this is quadrant 1. And if you have negative for both of these, this is quadrant 2 or 3. This is quadrant 1. Now, the thing that you need to notice about this shape, and I want to do a different color when I draw this, is that the actual shape of a 1 over x, if this is the x and the y-axis, is going to be a shape that will do something of this type right here. And you can plot the points. I'm not going to bother to plot the points, but what's most important that you need to recognize is that on the right-hand side, as you get closer and closer to x equals 0, and x equals 0 is this dotted line right here, this x equals 0 is a vertical asymptote. I'll write that out for you later. Well, it's actually written sort of over here. I'll write it again later. And what's interesting about this particular vertical asymptote is as you go from the right towards 0, it goes towards positive infinity. As you go towards the left, towards 0 from the left, it's headed towards negative infinity. So this is what's meant by the graph is approaching the vertical asymptote in opposite directions. So function approaches the vertical asymptote in opposite directions. And this is important that you recognize this, because that's going to be because this power up here is to the first power, an odd power. So because that's an odd power, for that number that you've excluded, that's going to have the vertical asymptote, or the graph approach the vertical asymptote in opposite directions. Now, when you have 1 over x squared, it doesn't matter whether you put a positive or a negative in there, you're going to get a positive out because of the fact that you're squaring those numbers. So 1 over 2 squared gives you 1/4, and here 1 over -2 squared gives you a 1/4. So this is quadrant 1 because they're both positive. And this one is quadrant 2 because it's negative for the x and positive for the y. So now what happens for this, and I'll show you with a graph again. Here is our x and our y-axis like I did before. And then if we do a different color this time so you can tell the difference, then as you get closer to the x equals 0, this vertical asymptote right here at x equals 0, it's going to head towards it in this upward positive infinity direction, and it's going to do the same thing on the other side. So in this particular instance, because this is an even power right here, an even power for that number that's excluded from the domain means the function is going to approach the vertical asymptote in the same direction. So maybe I'll show you a picture later sometime of me doing the dance moves for a vertical asymptote that has a odd power, and then a dance moves for an even power, because you don't get that pleasure to see it. So maybe I'll just take a picture, have my daughter take a picture and show you that. So again, all of this is to show you vertical asymptotes, and they occur when a number is excluded from the domain. Most of the time, you'll see examples when there's holes later, and then we are going to show lots and lots of examples that I'm going to hit the highlights of, and we're going to do. So this video may be a little bit longer because I like to do lots of practice and examples for this. Now the next thing I need to talk about are horizontal asymptotes. We already talked about vertical asymptotes on the previous page, previous slide. Okay, previous. Now we're talking about such fun. Now we're talking about horizontal asymptotes, and there's three cases. I couldn't fit all three cases on one piece of paper, so I went ahead and did two pictures. So you'll see case number two twice. But the thing about end behavior is that it's going to be concerned based upon the dominant term, just like the dominant term you had back in polynomial functions back in section 3.2. Now you have two dominant terms that you have to worry about. So you have a numerator that has a dominant term, you have a denominator that has a dominant term. So I take those two numbers, those two dominant terms, and I take them and I make an equation out of them, y equals, because it's going to be some kind of line most of the time. And what will happen is the x squareds reduce out, and you're left with this number, y equals 3. So that is your horizontal asymptote. So what can happen is that the x's reduce out, and you're left with a number, and that is your horizontal asymptote, which you'll see me write this frequently when we do other examples later. Now when I take the dominant term here and the dominant term here, and I do the same thing with this, what happens then is I reduce it, and what I want you to recognize here is that as x gets bigger, then what happens to the y? Well, 1/2, 1/4, 1/6, 1/10, as these x's get bigger, the y values get smaller. Okay, so they get smaller. And because of that, you don't have a particular number, or you do have a particular number. It's y equals 0 is going to be your horizontal asymptote, which you might want to also make note is the x-axis. That is your horizontal asymptote. Why? Because these graphs, or these points right here, get closer and closer to that, and they never quite reach it, and they will not quite touch that horizontal asymptote. We'll talk more about that in just a second, but you either have a number like this where it reduces completely the x's, or you get a situation where there's an x in your denominator. And one of my students years ago said, well, if I just see that, then I know that the horizontal asymptote is the x-axis, and he's 100% correct. That would work. Now let's keep going to the next slide. So here's what we already talked about right here. And again, as this gets smaller, I'm talking about the y values get smaller, then I know this heads towards y equals 0. Now, when you look for the horizontal asymptote this time and you take the dominant terms from these two and you look at what's left, what's going to happen is you end up with an x in your numerator instead of your denominator. So as x gets bigger, the y also gets bigger. So it's not getting close to one particular number like a 0, it's getting close to some other kind of shape. And this other shape is what is called an oblique asymptote. How you find the oblique asymptote is something you probably thought you never were going to do again from intermediate algebra, and that is to do long division. So we're going to do long division to remind you how to do that. So to get the oblique asymptote, what I'll have to do is take the x plus 3 and divide it into x squared minus 6x plus 1. So you focus in on the dominant terms. So you look at the x squared divided by x, and that gives you an x. So that's what I'll put right here as an x. And when I do that, I'll have to distribute that to both terms. And so the thing that you've got to not forget from your intermediate algebra days is to distribute the negative. And so I'm going to distribute the negative, just like I've been trying to do all along. I'm going to change those signs. These add out like we expected, and this is going to give us a negative 9x. So I bring the 1 down and I do the process again. So I take the negative 9x divided by x, and I get a negative 9. And so when I multiply that, I get a negative 9x minus 27. And I have to distribute the negative. So let's change the color so I can distribute the negative. So when I do that, this becomes a positive, this becomes a positive. These subtract out, and I'm left with a 28. So what that means then is that this equation that you started out with right here has no horizontal asymptote. It has an oblique asymptote. And that oblique asymptote is going to be of this form right here. We've changed this equation to look like this equation, and it is going to be, and I forgot to write the minus 9 here, it's going to be x minus 9 plus the 28 over x plus 3. So the oblique asymptote is going to be this line right here, y equals x minus 9. It is the non-remainder part of your division process. What do you do about the remainder? I'll explain that when we do an example later. So to find the oblique asymptote, you have to do long division. Alright, now I've got a set of examples that I usually lecture on in class so that you can listen and pay attention. And so my advice to you again is get a copy of that handy so that you can just make notes as to what I'm doing when I do this process. Now, as we discussed when we did y-intercepts previous to this, that all you had to do is look at the constants. So that's what I'm looking at right here, the constants. So my y-intercept is going to be the point 0, negative 1/2 after you reduce it. Then you have to look for the x-intercepts, and the x-intercepts are whatever makes the numerator equal to 0. So next time I do this, I'm just going to say n equals 0 is how you're going to tell that. Alright, so in this case, if you set 2 equal to 0, you get no solution. So no solution means there's no x-intercepts. So now we need to look at the vertical asymptote. And the vertical asymptote is going to be, let me get a different color. The vertical asymptote is going to be when the denominator is equal to 0. So I'm taking this denominator right here, and I want to erase some of that. And actually, let me erase all of that. And so I'm looking at the denominator, and I'm trying to figure out what makes that equal to 0. And the answer is x equals 4, and that's where I get this vertical asymptote. And because this exponent is to the first power, it's going to approach in opposite directions based upon what we talked about in slide number 1. Alright, so the next thing to worry about is the horizontal asymptote, which is the end behavior. And again, let me get a different color, and let me erase some of this so you can see it. The end behavior, I'm going to get that end behavior by looking at the dominant terms. So I would have a 2 over an x. Y is equal to 2 over x. There's nothing to reduce, and as x gets bigger, the y gets bigger, or smaller I should say. The y gets smaller, so it's getting closer to y equals 0. This n and m stuff is another way you could do it. That's just the degree of the numerator being x to the 0 power, the degree of your denominator being x to the first power, and if n is less than 1, you know you have a horizontal asymptote that's the x-axis. And that is the key thing. That is the x-axis. So when I check to see, does it cross the horizontal asymptote, and that's something I forgot to talk about, and I'll talk about it right now. Your graph will never crosses a vertical asymptote. And it's possible for it to cross a horizontal asymptote. So never, and it is possible to cross a horizontal asymptote. So how do I check that? What I have to do is I have to set the horizontal asymptote equal to the function. So 0 equal to 2 over x minus 4. If you cross multiply, you get 0 is equal to 2, which means no solution. So if there's no solution, that's telling us that the answer is no here. But if we were awake, we would have recognized that, because this says the horizontal asymptote is the x-axis, and this says we have no x-intercept, so it doesn't cross the x-axis, and that is another reason right there as to why that answer is no. Now, I need to erase some things so I can talk about graphing and deal with that. So let me get a different color. Let's talk about graphing. Now, when you graph things, you're going to graph the points that you know, and I only know this point right here, and I know this vertical asymptote at x equals 4 that approaches this in opposite directions, and I know the horizontal asymptote is this line right here. I didn't highlight it any more than that other than just labeling it y is equal to 0, so you can kind of see it there. All right, now what you have to imagine is this. Whatever lines or points you have drawn on this graph, they're like walls, okay? Can you go through a wall any place that you want? The answer is no, not unless you're Casper the Friendly Ghost. You cannot go through any point, or any line I should say, unless there is a point on that line. So a point might be a y-intercept or an x-intercept or a place where it crosses a horizontal asymptote. Those would be locations that will be like doors in a wall. So the next big question, if you understand that analogy, is this: where do I start? Well, I'll start at the I'll start at the y-intercept practically all the time. Well, when won't you start at the y-intercept? I won't start at the y-intercept if I don't have one, or the y-intercept is at the origin. That's when I might actually have to plug in a number to figure things out. So let's talk about graphing this now, and let's just do a dark green, I guess, for this. So I'm starting at this point. I know my graph is going to have to head towards that horizontal asymptote and get closer and closer to it. And then I know, because it never crosses the vertical asymptote, it's going to head down. Why doesn't it go up? Why doesn't it go like this up here? Because it can't cross it. There's no points there. Those points are not located here. So what do I do now on the other side? I don't have any other points. Well, I look at the fact that it's approaching in opposite directions and it's going towards negative infinity here or down, so it's got to go up or positive infinity here. And that means the graph is going to do this right here. All right, I have to pause to let my dog out. Okay, dog is outside. We're going to have a little fun with this craziness right now. So moving on to example 2. Example 2 is at the bottom of that page, and again I'm going to go a little faster, and then we're going to have 5 examples where we do it all of it together. So if you want to find a y-intercept, you can put a 0 into the function. You can do that, or just take the dominant terms, the constants. So negative 10 and 9 is going to give you this, which is the same thing as 0 and negative 1 and 1/9. I'll probably use mixed numerals when I do most of this. Let me erase this. Alright, so y-intercept's taken care of. X-intercept, I get that by setting the numerator equal to 0. And I will give them to you factored like I've factored them here, so you don't have to worry about factoring unless you do problems out of the book. Okay, so what I'll do then is set each factor equal to 0, and I get 5, 0, and I get negative 1, 0. And these are to the odd powers, so bouncing and going through still applies here. Now this too produces no x-intercepts, so I don't really worry about that. It's like saying 2 is equal to 0, and that doesn't produce anything. So that's a false statement, so there is no x-intercept right here. Alright, so let's go to a different color, and let's talk about what's going to happen now for the vertical asymptote. Well, the vertical asymptote comes from this denominator being equal to 0. And if I solve that, x minus 3 equals 0, I get x equals 3. And what's different about this is it's going to go in the same direction. Again, I'm going to share my cheerleading moves with you later, just as a joke for an email, so you can see what I'm talking about. Anyway, that's the price you pay for not having me in front of you. So we know the even power is going to indicate that that's going to approach that vertical asymptote in the same direction. The horizontal asymptote, we look at the dominant term because it's the end behavior. What a pain. So the end behavior, when I look at the dominant terms right here and here, it's going to reduce out. In other words, I'm going to have y is equal to 2x squared over x squared is equal to 2. This is how I teach it now. This is what I used to do back in the day, but what I used to do is take the highest power, the degree of the numerator, the degree of the denominator. If they're equal, then you just take the coefficients, and coefficients are, here is a right here, and here is b, which is a 1. So anyway, let me erase that stuff so it gets out of the way so you can see it better. But the horizontal asymptote is y equals 2. So that's what I would have for my horizontal asymptote. Now, whether it crosses the horizontal asymptote, I have to check that. It never crosses a vertical asymptote, but it can cross a horizontal asymptote. So I'm cross-multiplying. So I'm cross-multiplying here and here. And so if I distribute the 2 times this x squared minus 6x plus 9, I get this result. And 1 times that numerator is going to give me this result. And if I subtract 2x squared from both sides, this is gone and this is gone. So now it's just a matter of solving this. So I was running out of room, so basically what I did is I added 8x to both sides. And I also subtracted 18 from both sides. And that's what gave me this negative 4x minus or equals a negative 28. And so I get an answer. And because I get an answer, that means this is going to cross, and the place it crosses is the point 7 that comes from this, and 2, which is the horizontal asymptote right there. So that's how I get that information. Now when I graph this again, I would know my points here and here and here, plus this point at 7, 2. And that'd be information I know. I know my horizontal asymptote is this line, y equals 2. I know my vertical asymptote is x equals 3. So I would start at this y-intercept and I would go down because it can't cross this way because there's no points for or place for it to cross those lines. And then it's going to hit this x-intercept, go through and head towards its end behavior. Your graph always has to head towards that horizontal asymptote right there, whether it be from below or from above. Now because it's approaching the same direction, I know that it has to be down here, and it's going to come up, hit that point, and it's going to hit this point and go through, and eventually it's going to turn back around and head towards its end behavior from above. Now you might say, well, how do I know it's going to just go through right here? Well, I can tell you that the examples that we do and the problems that we do would have to be much more complicated in order for it to bounce off of that, okay, to do something like this. So we're not really going to have to worry about that happening. It's going to go through your place that it crosses your horizontal asymptote. There's example 2. So again, I'm going to get faster for different parts of this as we go. All right, so the third example, I had to move it a little bit back further because I had it over one page, so it's something I don't know if, ooh, look at that, I can make it bigger. And I need to erase that. All right, good job. And I'll make it smaller when I need to. Now here's the thing that's different about this. When you factor it, the domain, first of all, is going to be all reals except for a 2 and a 1. Now, what happens though is the x minus 1's reduce out, and so everything that I do is going to be using this reduced version that I'm writing in red right here. Everything I do uses that reduced version. So because I reduced it up here, that tells me that I have a hole at 1 something, and we're going to figure out what that something is going to be in just a few minutes. All right, now if we go through the rest of the process, everything I look at and answer for all of these things is going to be using the red reduced version right here. So when I look at the y-intercept, I'm looking at those two values. So I have 4 over negative 2, and I have the y-intercept as 0, negative 2. I look at the numerator, set that equal to 0, and that's going to be negative 4, 0, and it's going to pass through. I look at the denominator, set that equal to 0, it's going to be x equals 2, and it's going to approach in opposite directions because that's to the first power. Then I look at the horizontal asymptote. The horizontal asymptote, if I do it the way I explain it now, is it's x over x, and that reduces just to be a 1. So that is your horizontal asymptote, y equals 1. Now I have to see if it crosses the horizontal asymptote. So I set the function equal to the horizontal asymptote. And when I cross multiply this, I end up with x minus 2 equals x plus 4. The x's subtract out, and I'm left with a false statement. Because that's false, the answer is no, it does not cross. Okay, my graph will not cross that horizontal asymptote. Now what about the hole? Let's talk about the hole. All right, if I want to find the hole, I have to plug in that x value right there. So I'm going to plug it in to the reduced version, and I'll have 1 plus 4 over 1 minus the 2. That's going to give us 5 over a negative 1. And so that's the location of my hole. It's going to be at negative 5. And here's the calculation right here of the hole as well, if you look at the piece of paper later. So what I need to now do is just talk about the graph then. So let's see if I can move things. Oops. Let's get rid of that stray line. So again, when I start putting information on this, let's graph it with a nice, beautiful, let's see, purple. We haven't done purple. So I know this point, I know this point, and I know this hole right here. Okay, this hole is something that I'm going to put with an open circle to indicate. It's kind of like a sinkhole in the middle of a road. It's missing part of the pavement. So my graph is going to have to head towards this hole, and then it's going to continue on down because it can't go up. There's no way it can go up here because of the fact that there's no points or no doors on our lines right there. Plus it's going to have to head towards this point, pass through, and head towards our horizontal asymptote of y equals 1 from below. And because this is approaching in opposite directions, it's going down on this side. It has to be going up on this side. So my graph is going to go up right here. And you can see then our shape. And again, the graph is everything that you have for this equation right here. And then the extra thing is the hole that you would also need to include. The domain is everything but 2, 1. And anything that's excluded is going to be a vertical asymptote unless this reduction stuff happens right here. All right, let's pause it for a second. Okay, so here we go, looking at example number 4. And with example number 4, we're going to have this factor into x minus 2 squared over 2 times x minus 3 times x plus 1. I'm talking about the factored version right here. So the y-intercept is going to be whatever I get when I look at my constants. So it's a 4 over negative 6, and we're going to end up with a negative 2/3. Okay, the x-intercept comes from the fact the numerator is equal to 0, and because this is an even power, it's going to be tangent or bounce off of that particular x-intercept. So that's a bounce right there. Bounce. The vertical asymptote, when you set your denominator equal to 0, is going to have two of them. It's going to be x equals 3 and x equals a negative 1, and they're both going to approach it in opposite directions when we do the graph. This is what's going to be different about this particular graph versus the other example. The horizontal asymptote are going to be when you look at the dominant terms, and if you do it the way I explained it to you before, your dominant terms are going to be x squared over 2x squared. They reduce out and you end up with a 1/2. That's where that comes from, right there. Now, does it cross the horizontal asymptote? So if you set the horizontal asymptote equal to the function and you solve that, then the 2x squared subtract out and eventually end up with this answer. So it's going to be a yes. It's going to be at the point 3, 3 1/2, 1/2. It's listed right here, but I guess I didn't write it down as well as I should. Time to update these notes. So let's talk about graphing this. Let's get a different color. Let's do it in blue. So I have this point that it's going to bounce off of, because that's my x-axis right there. This is my y-axis. I've got my vertical asymptotes here, and they're going opposite directions. And I have my horizontal asymptote right here at y equals 1/2. So that's slightly above the x-axis. So I'm going to start here with my graph, and I'm going to go down because it has to go down. It can't cross either of those two lines here or here. And so then it's going to hit this point, bounce off of that, and has to head down because it has no way to go up. It can't go up because it's not defined there. There's no point identified there. Now, I also had a place where it crossed the horizontal asymptote that I didn't indicate, which was this one right here. So there's a point located there. So if it's going down on this side, it has to be going up on this side. If it's going down on the right-hand side, the left-hand side of x equals 3, then it's going to have to be going up on this side. It's going to hit that point and head towards that horizontal asymptote without touching the x-axis. So that should not be touching the x-axis. So I'm going to erase that so you can see it better with the black. So that's what it should be doing, and I don't think I can get my pen to show it properly. So that's what's going to happen with this graph. Let's do the last one so that we can eventually do our examples from beginning to end. Alright, so it's all factored for us. The y-intercept I get by the dominant terms like we've always done. My x-intercept I get from setting the numerator equal to 0. The vertical asymptote I set the denominator equal to 0. And that's where this comes from, and it's going to approach in opposite directions because that's to the first power. And then when we do the horizontal asymptote, what is happening here? Well, the way I explained it to you was x squared over x, that's going to reduce and give you an x over 1. So as x gets bigger, y gets bigger, that means there is no horizontal asymptote. None. But what you have is an oblique asymptote. And if you get into calculus someday, you will learn about oblique asymptotes could also be parabolas or other shapes as well. But we have an oblique asymptote. The way I get this is by doing long division. So guess I'll do long division to make sure you have it. Just put it right next to it so you can hear me talk you through it. So I have x squared divided in, or x plus 1 divided into x squared plus 2x minus 15. So x goes into x squared x times, so I'll multiply that, and I'll have to distribute the negative. So I need a new color. When I distribute the negative, changes those signs, so these head out, and I'm left with an x. Then I bring the minus 15 down, and I do it again. So if x into x goes one time, so I get x plus 1. I have to remember to subtract that, so let's get a different color. And when I distribute the negative, I end up with a remainder of negative 16. So the oblique asymptote is going to be y is equal to x plus 1. So you need to graph that. Dotted. Has to be dotted. And that's what I did with the slope of 1 over 1 and a y-intercept for the oblique asymptote of being a 0, 1. So there's the y-intercept. Here's my slope of going down 1 to the left 1, or I could go up 1 to the right 1, and that's where I got this line right here. That's my oblique asymptote. So you might wonder what happens to the negative 16. The negative 16, that remainder that you have of a negative 16 over x plus 1, that is the distance that's keeping the graph from touching that oblique asymptote. So that's what that is going to be involving. The rest of the information I'm graphing like we've done before, vertical asymptote like we've done before, all of that is the same, approaching in opposite directions. And so now when I graph this, I'm going to follow the same process that I did before in terms of where I start. I start here, it has to go down because it can't go up here. Then it's going to come this way, cross that x-intercept, and head towards its end behavior, which is the oblique asymptote. Then here's a point that I have, and it's going to approach in opposite directions. So if it's going down on this side, it has to be going up on that side. And that's what's going to happen right here, is the graph is going to be on this side. And again, that remainder part is that distance that it's keeping from touching the oblique asymptote. Now again, some of you may wonder, can it cross an oblique asymptote? And the answer is yes, it can. If you ever get bored, come visit and I'll show you how to check for that. Basically, you set this equation, x plus 1, equal to this equation, and solve it if you can. But again, I can safely tell you they're going to be much more complicated than what you see right here. So that's the basics. I'm going to get a swallow of water, and I'm going to show you 5 examples relatively quick so you can practice them yourself later. Alright, here we go. 5 examples that you may want to try on your own before you do any of the watching of the video, and you can check your work. But there'll be lots of other examples in worksheets and in the book that you can try. So my y-intercept is going to be the point 0 and negative 3 over negative 15, which is going to reduce to be 0, 1/5. And that's what I'll graph. The x-intercept, I think I need another color. The x-intercept is going to be 3, 0. It's what makes the numerator equal to 0, and it's going to pass through. The vertical asymptote is going to be 2 of them, x equals 5, opposite directions, because the odd power, and x equals a negative 3. If I was in class, I would emphasize that these are points, so you write them as ordered pairs, and these are lines. Whoops, this is a line, and this is a line. Okay, and I'd want you to write those as equations of lines. Don't you dare write them as ordered pairs. So how do I get the horizontal asymptote? I take the dominant terms, and I have x over x squared. It reduces to be 1 over x, so that means I have a horizontal asymptote that's y equals 0. Does it have a hole? And the answer is no, because I didn't reduce anything. So not applicable is what I would say for you. And by the way, this form that you see, I took this off of a test, and this is the kind of thing that you'd be filling out and trying to put the information that you're doing right here. Now, does it cross the horizontal asymptote? Well, I'm awake. I hope you are. This is the x-axis. This is an x-intercept, so the answer is yes, and you're not going to stop there. You're going to tell me where. And so that's the information that I need to know to graph this thing. Let's go back to red. So I'm going to graph the different pieces of information that I have. I got a positive point right here. Oops, that's way too big. And let me erase that. Too big. So I have a point right here. And let's see, 3, 0, I have a point. I have a line at x equals 5. It's approaching in opposite directions. I have another line at x equals a negative 2. It's approaching in opposite directions. I have a line that's y equals 0. And I think I better do my points in a different color again. So I have a point that's located right here. I have a point that's located right here. I hate you. Alright, so that's good enough for us to graph this thing. So let's graph it. I'm going to start at this y-intercept, and I know the graph is going to have to go up in this situation right here. Then it's going to swing around and hit this point and go through and head on down to its end behavior. It cannot cross that line right here. No way for it to cross. Alright, then I'm going to focus in on one side or the other. This is like in Detroit, this is like in Tampa. So I'm going in Detroit, I'm going down on the left-hand side. That means I have to do the opposite on the right-hand side, and that's what I'm doing. Okay, now I'm in Tampa, so I'm going up on the right-hand side. I have to be going down on the left-hand side, and there's my graph. Okay, so let's move on to another example. Different color. Let's see, let's just do all of it in green. So the x-intercept, I need to move this just a tad so you can see it. The x-intercept, or y-intercept I mean, is going to be 0 and 4 over 8, which is the same thing as 0 and 1/2. My x-intercept is negative 4, 0, and it passes through. Vertical asymptote, I have two of them again at x equals a negative 4, opposite directions, and x equals a negative 2 in opposite directions. But you know what I did? Oh, I made the mistake. I'm just such a hurry to get this done, I forgot to do something. What in heck did you forget to do? I forgot to reduce. What do you mean you forgot to reduce? The domain is going to be all reals except for a negative 4 and a negative 2. But this reduced right here, so everything that I do should have been in the red edition of this function. And so everything I do should be 1 over x plus 2. Does that change the y-intercept? No. This isn't correct, but doesn't change the y-intercept. Does it change the x-intercept? Heck yes, there is none. Because 1 is never going to be equal to 0. Does it change the vertical asymptote? Yes. No vertical asymptote here. You're going to have a vertical asymptote at x equals a negative 2. That's still there. But what's going to add to this is that you do have a hole. And you have to tell me where that hole is at. It's at the point negative 4 something. And you have to tell me where that something is. So let's figure it out now. Half of a negative 4 is going to be 1 over negative 4 plus 2. This is going to work out to be a negative 1/2. My hole is going to be at negative 4, come on, and comma negative 1/2. And as far as my horizontal asymptote is concerned, if I take the dominant terms from that red equation, that's telling me my horizontal asymptote is the x-axis. And the answer to this is no, it doesn't cross because we have no x-intercepts. So, kind of glad I made that mistake because guess what? That's what you're going to do. Sometimes I'm devious like that and I actually make them on purpose, but I won't admit to that this time. So I have this point at 0, 1/2. I have this line at x equals a negative 2. Let's see if I can get it dotted. It's approaching this in opposite directions. I have the point that's at -4, -1/2. Let's make this a different color so you can see it. And so that -4, -1/2 is going to be this point right here. And when I actually graph it, I'm going to do it a different color of everything here. But I also have, I have a horizontal asymptote that's going to be this line right here, the y equals 0. So let's go ahead and graph that now in green. So I start at this point. It's going to have to go up because it can't cross the line here. It's going to head towards end behavior from above. And then I know that it has to approach it in the opposite direction, so it's going to come here, hit this point, and then approach its end behavior from below, which is the horizontal asymptote y equals 0. All right, we're almost done. I've got 3 more examples. All right, so I need to make sure I don't have any holes, and no reducing right here. No reducing. So I'm ready to go ahead and just work with what you see nicely factored for us. So y-intercept is going to be what amounts to a 0 and a -12/4, which I'm going to write as 0 and -3. That's what I'm going to graph. X-intercepts, I have 2 of them. I have one at -4, and it passes through because of the odd power right here. Shoot. All right, and then at 1, 0, it's going to pass through. Maybe you can see the power better there, but it's the same thing here. Pooey, there. All right, so vertical asymptote is going to be x equals a -2, and it's going to approach it in the same direction because of the even power that you see right here. Does it have a hole? No, so it's not applicable. Just say that. The horizontal asymptote, if you take the dominant terms, are going to be reducing, and you're left with a y equals 3. Is it going to cross? Well, I have more work to do. So I'm going to see about making this smaller. Oops, not that small. All right, I give up. I'm just going to try to fit it right here. And I'm going to set 3 equal to that function. And I always use the unfactored one because I would just have to do extra work if I use the factored one. So when I cross multiply, this first one stays the same, so I have 3x squared plus 9x minus 12. That's equal to, when I multiply this one, I'm just going to multiply it. I'll have 3x squared plus 12x. Okay, phone stopped. When I multiply 3 times 4, this will be 12. So these things subtract out. If I subtract a 9x from both sides, and I subtract a 12 from both sides, I'm going to end up with a -24 is equal to 3x. So when I divide by 3, I actually get x is equal to a -8. So it's going to cross at -8, 3. Alright, so I'm going to graph my lines in red so you can see them, and I'll graph points in a different color so you can see those. So let's see, my line would be at x equals a -2. Y equals 3. Alright, graphing my points, -8. Well, it's kind of off the charts, but I'm not going to give up. Here's a -6, -7, -8. So I'm going to have this point all the way out here. And I'm going to try to draw a big one so you can see it. Looks like I need a different color so it doesn't merge in with the green. I also have 0, -3, so I have this point. And then I have the point -4, 0 here. And the point 1, 0 here. So let's get a different color so you can see it. Let's see, I guess blue will work. So I'm starting here, and I know it has to go down because it can't cross either at this line, the x-axis or y equals 0, or this line. And so it's going to head up here, go through, and head towards its end behavior from below. Now, because it's approaching the same direction, it's got to be down here. It's going to hit this point, go through, it's going to hit this point, and then head towards its end behavior from above. And yes, you ought to keep going and graph the whole thing, even if it's off the charts here. I try to make decent sized graphs, but unfortunately, they're not all perfect. So let's see if we can keep going here. All right, green. So y-intercept here is going to be the point 0, -6/5, which is the same thing as 0, -1 1/5. X-intercept is at 3, 0. It's whatever makes the numerator equal to 0. It passes through. Vertical asymptotes, we have two of them, at x equals 5 and at x equals 1. And there's no hole, so I don't have to worry about filling this in, not applicable. As far as my horizontal asymptote, if I take the dominant terms, this reduces, leaves me with a 2 over x. So as x gets bigger, y gets smaller. That means my horizontal asymptote is the x-axis, y equals 0. So does it cross? Yes, it's going to cross at the x-intercept at 3, 0. Don't need to do all the work for that. All right, so let's graph the lines in red. So I have x equals 5, which is over here, and approaches this in opposite directions. I have x equals 1, which is located right here, opposite directions, and I have y is equal to 0, which I don't want you to think there's points there, so I'm just going to put it and extend it right here. All right, let's graph the points in a different color. And the points that I have are going to be located here, 3, 0, and that's all the points that I have. This is a 0 right here in case you're wondering. Not going to worry about the color. All right, let's graph it in green. So I start at the y-intercept. I know it has to go down, and then it's going to head towards the end behavior and not cross anywhere. Now it's going down on this side, so it has to be going up on this side. So it's going to head towards that x-intercept, cross it because it says go through, and head on down because it can't turn back around and cross back up here. Not able to do that. So I have that portion taken care of. So since it's going down here and it's approaching in opposite directions, it has to be going up here. And there is example 4. And I'm determined to make this under an hour, so let's keep going. Green. All right, y-intercept is going to be, oh my goodness, it's going to be 0, -12. I think I'm off the charts with this one. Anyway, the x-intercepts are going to be 4, 0 passing through, and a -3, 0 passing through. Vertical asymptote at x equals a -1 going in opposite directions. Does it have a hole? No, not applicable. Move on. Horizontal asymptote doesn't have one because you end up with an x in your numerator, so there is none. But we don't have to check to see if it crosses. We're not going to worry about doing that. I'm not going to give you one that's that complicated, but what you will have to do is find the oblique asymptote. So to find the oblique asymptote, you have to take x plus 1 and divide it into x squared minus x minus 12. So x goes into x squared x times. I get x squared plus x. I have to distribute my negative. So this changes. So these subtract out. I'm left with a -x, a -2x actually. I bring the -12 down and I do the same thing we just did. X goes into -2x a -2 times, so I get a -2x minus 2. I have to subtract. So different color, change this to plus the opposite. These add out, and this gives me a remainder of a negative 10. So my oblique asymptote is y equals x minus 2. The equation itself is x minus 2 is an alternative form plus a negative 10, not 16, negative 10 over x plus 1. We don't care about this. What we care about is the x minus 2, this equation right here. So let's graph that. I know that that's a y-intercept of 0, negative 2, and I know the slope is a 1. So I have this point down here, and I have a slope of 1, so my graph is going to do something like this, is my oblique asymptote. And I have this bad feeling I need to keep going way down here. We'll definitely have to graph the rest of this in different colors. X equals a negative 1 is going to be this vertical asymptote right here. Approaches in opposite directions. And then the points that I have, let's do that in different color. Let's do it in some form of red. So I have a point right here. I have a point right here. And then 0, negative 12, I'm just going to estimate is down right here. I'm not going to take the time. Come on and make a point. All right. So let's see. Let's graph it in a different color. I think I want to do purple this time for grand finale. So I'm going to start at this y-intercept. It's going to head down. It's going to head towards that x-intercept, and it's going to head towards the oblique asymptote from below. Because it's going down on this side, it has to be going up on this side and going through that x-intercept and heading towards that oblique asymptote from above. All right, so hopefully you handle this. I hope the rest of my lectures are going to be a lot shorter than this. So off we go.